Hi, welcome to Mr. Tompkins' physics class. Today we're going to talk about types of forces. And in this section it's going to be change in motion. Now a force is a dynamic influence that causes an acceleration or a change in the object's velocity. Dynamic means that a force can change depending on what's acting on the object or what's causing the force and where the object is located at. Forces are vector, and they have it, which means they have a direction and they have a magnitude. Their direction is determined by the accelerations that they cause. And the units of force are newtons, named after Sir Isaac Newton. And one newton is roughly 0.225 pounds. We'll use that conversion later on, but right now just keep in mind that roughly 4 newtons is a pound. Now, because a force changes an object's velocity, that means even changing the direction of travel requires a force. So we can use this to determine what causes forces on your car. Now we're talking about the forces on your car that your car can do, or that you will manipulate your car. Not kicking your car or pushing on your car, but what you can do to your car to make it cause a force on itself. The first one is the easiest, and that's to cause a force is to cause an acceleration or push on the accelerator. You push on the accelerator, the car accelerates in the direction of your velocity. So the acceleration and the velocity point in the same direction. And we've talked previously about how if those two agree in direction, then the car is going to speed up. Another thing that you can do to apply a force to your car is you can press on the brake. This causes an acceleration in the opposite direction of your velocity, which will cause the car to slow down. And then the third thing that you can do, and the one that's most not thought of, is just turning the steering wheel. So turning the steering wheel changes the direction of your velocity, but it doesn't necessarily change your speed. So by changing the direction of the velocity, we are also causing an acceleration, which means that we are also applying a force. Now there are two types of forces, two main types, two categories. The first type is contact forces. Now these are your everyday pushes or pulls, and they require an object to be in contact in order to apply a force. The next type is field forces, and these are more like the Star Wars movies. We can actually cause accelerations or manipulate objects from a distance. The first one is gravity, and so here's a guy, the apple falls, gravity pulls the object down. The earth does not have to be in contact with an object to apply the force. The second type is this type right here. It is called the electrostatic force, and that is caused by electric charges. This is why your hair stands up whenever you touch a Van de Graaff generator. And then the third field force is the magnetic force, which is able to manipulate objects using magnets. So let's start with the field forces. Now the first field force I want to talk about is the force of gravity. The force of gravity always acts on an object, and it always points towards the center of the earth. Even if you're in outer space, the force of gravity is still acting on you. It appears as though you're weightless, but you're actually not. The variable that we give for the force of gravity is going to be a capital F and a subscript of a lowercase g, which stands for the force of gravity. Now in this scenario, I have a block that's on a horizontal plane, and then I have another block that's on an inclined plane. If I were to draw my force vectors on these blocks, they're going to point straight down. I also want you to take a look at the magnitude of the force vector whenever the object is on the horizontal plane. Because whenever I draw the force vector of the same object when it's on an inclined plane, it's going to be the same size. It's going to point straight down towards the center of the earth. So if you have the force of gravity, no matter where the object is located, as long as it's on Earth, the force of gravity is always going to be the same, and it's always going to point straight down. The next type of field forces we're going to talk about is going to be the electric force. This is the force between two objects caused by differences in electric charge. And it's what makes your hair stand up, like I previously said. Now this follows a rule. The rule is opposites attract and likes repel. In this scenario, the top one here, I have a positive charge that is being attracted to a negative charge, and they get pulled together. In the second scenario, I have two like charges, two positive charges, and whenever I bring them close together, they want to repel and push apart. This is the part that causes your hair to stand up. Your hair gets a positive charge on it, and then they repel each other, so they try and get as far away from each other as they can, and they stand up to get as far away. The third field force is the magnetic force. This is caused by moving charges, and so they're somewhat related, but in this instance, there's a different field established. The magnetic force acts just like the electric force, except that instead of calling them charges, we call them poles. You have a north pole and a south pole. Opposite poles attract, and like poles repel. Let's move on to the contact forces. Now we're going to break the push and the pulls down into more specific types of forces. The first one I want to talk about is the normal force. The normal force is given by a capital F with a subscript of a lowercase n, which stands for normal. Now, normal in your math class is what is used to describe a perpendicular force. So the normal force is always going to be perpendicular to the two surfaces in contact. So I have to have an object sitting on a surface. Now, this force is what causes or what stops an object from accelerating through another object, is the normal force. Whenever I put an object on a table, the force of gravity is pulling it down, but the normal force prevents it from going through the table or accelerating downwards. Now, this first scenario here, I have a block sitting on a table, and if I were to draw the normal force, it would look something like this. Notice its magnitude, and notice that it's perpendicular to the surface or the table. Whenever I move over here to the inclined plane, same block, same weight. But in this instance, the force, the magnitude of the force is less. All right? You need to know that the normal force can change depending on where the object is located at. But still notice that the normal force is still perpendicular to the surface of the inclined plane. And then thirdly, if I were to take this angle here and I were to rotate it, make it an extreme angle all the way around so that this object was being pushed against the surface of the ceiling. Once again, the magnitude is going to be different depending on how much force is applied to the block by whatever's holding it up there. But also, notice that it's still perpendicular to the surface. In this case, it points straight down. The second type of contact force is going to be the frictional force. It's going to be given by a capital F and with a lowercase subscript. There are two types of frictional forces. There's a static frictional force and there's a kinetic frictional force. We'll talk more about those later. But these are forces caused by an object sliding or wanting to slide across each other. There has to be two surfaces in contact, and the object must want to move or is moving. Okay? In the first instance, if I wanted to push this block here that's sitting on the table to the left, then the normal or the frictional force is going to be to the right. So if the block wants to move to the left, the frictional force is going to be in the opposite direction, which is to the right. Likewise, if I want to push the block to the right, then the frictional force is going to be to the left. This just happens to be parallel to the surface, the two surfaces in contact, and opposite the direction the block will want to move. If I move over to the inclined plane, so consider this like a slide, and this block wants to slide down the plane. Well, because the direction of motion wants to be down and to the left, the frictional force is going to be parallel to the slide, but up and to the right. Frictional forces are dependent on the two surfaces in contact, and we'll learn that later, exactly how we do calculations with that. The third type of contact force is the tension force, which is given by a capital F and a subscript of T, which stands for tension force. And this is any force that is applied to an object by pulling on a string. And it's always going to be along the string. So here I have my block. It's suspended between two wooden blocks, and I have strings holding it up. Now my tension forces will point along the strings, and up and out, away from the block. All right. And then our last type of contact force is going to be our applied forces. This is just given by the variable F sub APP, or force applied. This is any push or pull that we haven't discussed. This would be like if you were the one applying the force, or if the brake was applying the force. These are applied forces. Oh, this is not the force we're talking about. So let's talk about this idea of net force. Now, forces are vectors, and so we have to use vector addition whenever we start talking about net forces. Net force is just the sum of the vectors, or it's the sum of the forces all added together. For now, it's sufficient to look at the head-to-tail method for adding the vectors, and we will do that now, and then later on we will talk about the mathematical vector addition that we've talked about before. So in this instance, I have this black vector which points up and to the right, and then I have this red force vector that points down and to the right. And if I add them together using the head-to-tail method, I'm going to take the tail of my red vector and I'm going to place it on the head of my black vector, and it's going to look like this. Now, whenever I add these two together, my resultant comes out to be this yellow vector, and we can see that whenever I move it over, it's going to go from the tail of the black vector to the head of the red vector, just like that. And so my resultant, or my net force vector, is going to be the yellow vector. In order to fully understand net force, we have to understand, well, what does net force cause? And so net force is going to be either described as, if I have a net force, it'll be called an unbalanced force. If I don't have a net force, then it's going to be a balanced force. Whenever I add them all together, I get the net force. If there's an unbalanced net force, or the net force is not zero, then the object will accelerate in the direction of that net force. If the object is accelerating, then we know there has to be a net force. So there's kind of like both sides of that coin. So if the object is accelerating, then there has to be a net force. If the object has a net force, then it's going to be accelerating. Likewise, if the net force is zero and it's acting on the object, or the forces are balanced, then its velocity does not change. That doesn't mean it's not moving, but its velocity does not change. So it can be traveling at a constant velocity and still have a zero net force. Likewise, if the velocity doesn't change, we know that all the forces on the object have to cancel out. And that means the object is going to be in a state of equilibrium. And we'll talk more about what equilibrium is later. We'll do calculations with it. But right now, it's sufficient to know that if it's in equilibrium, then all the net forces have to cancel out, or they have to be equal and opposite. Free body diagrams. Now, a free body diagram is a tool used to analyze forces that act on an object. We use it to determine which direction and how much net force is on that object, as well as what objects are applying the force. There are 3 steps to making a free body diagram. Step 1, represent your object as a single point. We usually call this the center of mass. This is where we can sum up all the weight of the object into one dot in space. Step 2, determine what forces are acting on your object, their directions, and their relative magnitudes. Some people like to break this down into looking at the field forces first and then the contact forces. We will look at that also. And then step 3 is you're going to draw your force vectors on the point, on the single point that you summed up all your object to be. So here we go. We're going to do an example. Now, in this case, the object is being pushed to the right. It shows that it's accelerating because this is its initial position, and then the lines get further apart as it moves to the right. So let's look at how we will draw this free body diagram. Step 1, represent your object as a single point. This point represents my object, the center of mass of my object. Steps 2 and 3 we're going to do together. Determine what forces are acting on my object. Well, there's always going to be the force of gravity. Now, gravity always points down. So in this case, it points straight down, and it's given the variable F subscript g, or F sub g. The normal force, in this case, is always going to be perpendicular to the surface, And because the block isn't moving up or down, or its vertical velocity is not changing, then I know that it has to equal the magnitude of the gravitational force. So here's my capital F with a lowercase n, and my red vector is my normal force. Now, because the object is sliding along a surface, I know that there has to be some kind of friction. The object is moving to the right, so friction has to point to the left because it's opposite the direction of motion, but also notice that the friction vector has to be parallel to the surface. So the normal force is perpendicular, the frictional force is parallel. And then I am applying a force. All right, because it told me that in my scenario, and also because the block is accelerating to the right, there has to be an applied force. And it has to be larger than the friction because the block is speeding up. Look at the motion lines. Once again, it's accelerating to the right. So that means I need to have a net force to the right. And if I were to add my frictional force and my applied force together using the head-to-tail method, I would end up with a net force to the right.